So far, except in the last section, so far we have studied the mechanics of the object that can be approximated as the particle. Shape of the object is not our concern, since we can approximate the object as a particle, and the particle has no size, has zero size. So we don't care about the shape of the object. But in the real situation, the shape of the object has some effect. In this section, we will briefly study the effect of the shape of the object. The question is that what will happen when an object can be deformed, or it can change the form, if the object can change the form. As a simplest example, let us consider an object which consists of a block attached with a spring. So if we have a block and this block is attached with a spring, and we place it on a horizontal plane. Next, we will define the system, our system. As the block and the spring. Now, if we push our system to a wall, this wall, okay, we know that the spring will be compressed. So it means that the system deform, the shape of the system change when we push, or we push the block against the wall. So the situation will be like this. Okay, so you can see that the system deform, because here we define the system as the block and the spring, and the system deform. We know that when we compress the spring, there is the force from the spring exert on the wall, and also from the third law we know that there is the force from the wall exert on the spring, which means that there is a force on the wall exert on the system. We can also think that this Fs is the force from the system exert on the wall, and this Fw is the force from the wall exert on the system. It is interesting that in this case, the point that we have the force exert on the system is this point, and this point does not move. What happened is that the system deformed, changed the shape. But the point that the wall exerts the force to the system does not move. That is a very important point. Next, after we push the system like this, we release the system. So, what we will have is that the system, which is the spring and the block, will move away from the wall with the velocity v. Okay. So it means that when we release the system will gain the kinetic energy which equal to the half of the mass of the system times v square. So the system gain the energy, the kinetic energy. But where is this kinetic energy come from? You can see that we have the we have the force Fw exert on the system. Someone may say that, okay, we have there's the work done from the wall to the system, but be careful. You can see that the point that the wall exerts the force to the system is this point, and this point does not move at all. So it means that if the force, we know that there is a force on the system, but the point that the force applied to the system does not move. Work done by the external force, which is the force from the wall here, is zero. Remember, from the definition of the work, we have that work is equal to F S. Put it in the simple form because the force and the direction of the motion, I use the form that the force and the direction of the motion are the same. This is very simple. But the point is that the distance S here is the distance that the point that the force exert on the system move. Okay, so in this case, the point that the force exert to the system does not move. So in this case, W is zero. The question is that if there is no force, if there is no work on the system, we cannot use the work kinetic energy theorem to explain the energy gain in this question, in this problem. So in this case, we can say that work kinetic theorem cannot be applied Okay, so how can we explain the situation? The important point in this situation is that the kinetic the kinetic energy gained by the system comes from the internal potential energy when the system deform. Okay. The kinetic energy gained by the system comes from the internal potential energy when the system deform, and we can consider it as the potential energy, the elastic potential energy in the spring. So we have that delta E of the deformation is equal to the minus of the change of the potential. The potential decrease, right? Because it changed to the kinetic energy, and this equal to the change of the kinetic energy. Again, we can write this equation as delta K plus delta U is equal to 0. It means that we still have the conservation of the energy. The conservation of the energy still be applied, but the work kinetic theorem does not. We also have that the conservation of momentum also valid, or we can write down the impulse momentum theorem as usual. That is M delta V is equal to the F integral of Fw dt. That is, the change of the momentum of the system is equal to the impulse from the external force. Okay. And we have that P TOT is equal to the impulse. The impulse applied by the wall. This is the impulse applied by the wall to the system. Change the momentum of the system and make the system move, as we have discussed.